All right, so let's go ahead and get started. I think the room's just about full and we're just about at time. I'd like to start off and first thank everybody for coming, both to this session and coming up here to build. It's super awesome to host everybody up here and see everybody on campus. Today we're going to be talking about developing big data analytics applications with JavaScript and .NET for Windows, Azure, and Windows. That title's a bit of a mouthful. We like to have a nice big title on the session. What we're really going to be talking about today is how we can leverage Hadoop on Windows using HD Insight, particularly with a pivot towards JavaScript as well as .NET development. My name's Matt Winkler. I'm a program manager up here on the Hadoop team, so I've had a pretty cool job the last 12-ish months where I've been working to get Hadoop onto Windows. Suffice to say, it's been an interesting challenge bringing a set of Microsoft engineers up to speed on this big, giant Java application, and that's what we'll be talking about a little bit today. First, a little bit of context for me. How many folks are using Hadoop right now? Okay, cool. So there's about 10-ish of you. How many folks are thinking about using it in about, say, the next 6 months? A few more folks. Okay, that tips us over half. So talk today is going to be a little bit of Hadoop introduction for those of you who aren't familiar with Hadoop, set some context there, and then we'll dive into how we're using JavaScript and .NET as part of the Hadoop ecosystem. And so what I want to start out with, we talk about big data a lot, and I want to really kind of ground this with what exactly is it that we mean when we say big data. This is kind of a very big buzzword. I think the Harvard Business Review was in the front of all the airport kiosks about a month ago with everything CEOs need to know about big data. But it's kind of an important pivot with how we're shifting in terms of how we think about data. And the thing that grounds it for me is the Large Hadron Collider. This is a little device that's over, I think it sits in 2 or 3 countries. The bulk of it is at CERN in Switzerland, but I think it's close to the border. And this is all about doing super cool physics stuff that I don't understand, trying to find the Higgs boson and all these sorts of things. But the thing that really is impressive to me is that when this thing's running, it can output about a petabyte of data a second. Let that just sink in for a bit. That's a lot. And it's a lot in a couple of dimensions. The first is simply thinking about a petabyte of data. That's a lot of hard drives. Even if I go buy 3 terabyte drives right now, I need 333 and a third of them in order to be able to write this down, and that assumes none of them break. So there's kind of a volume of data that's pretty substantial there. The second one, though, is this what's after the slash. That's not just 1 petabyte, it's 1 petabyte every second. And so that means in the time that I've been talking, we're probably up to about 60 petabytes, or 1,800 hard drives. That's a lot. And so you can think about, when we say big data, it certainly means volume, petabyte scale. But it could also mean velocity. How rapidly is this data coming in? Is the data shaped funny? Is there variety to it? Is it unstructured? These are things that all kind of fall under this umbrella when we say big data, and the things that have evolved to help us understand these, as well as compute and process on top of these. Now, when I've given this talk before, the general response is, I don't have a Large Hadron Collider in my backyard, which is unfortunate. Everyone should have one. They're great toys for the kids to play with. But what I want to do is, it's not just scientific computation. It's not just this kind of what might seem like a niche scenario here. There's a lot of data that our apps generate, that our businesses generate, that right now we may be throwing away because we either A, don't have any place to put it, or B, if we have a place to put it, we don't exactly know how to get something useful out of it. And I'd like you to think about the different things present in your apps and in your businesses, whether that's sensors in a manufacturing setting, whether it's application telemetry. If you think about what we've done with Windows 8 in terms of learning how people are using it, I have the ability now to store clicks, to store the flows of people through my applications, and I can eventually go and try and understand my app better. Dave Campbell talked yesterday in the keynote about a scenario of, I've got this really great video application, but I want to be able to understand how my users are using it. So I can figure out, in a data-driven way, where should I go invest my dollars? The scenario that we talked about in the keynote yesterday was, hey, I'm finding out that people are really only watching 1 or so videos in my video app. I want to keep them engaged, because that's how I'm going to monetize my application. Well, how do I go do that? I can spend some dollars on fancier UI, I can spend some dollars over here, but if we look at how people are using the app, we can learn, oh, they're falling off after this. Maybe I should go write a recommendation engine. Maybe I need a way to get them more engaged. Once I write that, it starts this very nice virtuous cycle of making my app better. And it's data-driven. And so these things are all over, whether that's weblogs or transactional records, or if we've got call centers, we've either got transcripts of those calls or we've actually got the recordings of those calls. And I'd like to understand customer sentiment. These are all things that we have that we can start doing some interesting stuff with in order to understand our customers better, understand how our applications and our systems are working. And so if you think about something like Hadoop, really there's two places that Hadoop came from. One is a physics problem, that petabyte of data that I talked about, and the other one is an economics problem. Again, that petabyte of data, how do I store that cheaply? Right? If I go price out a SAN solution right now to store a petabyte of data, there's a chunk of change tied up in that. Are there cheaper ways that we can do this? Because what happens, I'm only going to keep data around as long as it's affordable for me to keep that data around. And so that's two things. That's a cost, and that's how much value can I get out of it. And so we want systems that let us get a lot of value out of that, and we also want systems that keep that cost down. And so this is really where Hadoop came from. Little bit of history. If you rewind about 10 years ago, there were a number of folks who were doing some interesting things early on in the big data space. They were primarily folks who were doing web search problems, and then intelligence agencies who happened to also have lots of unstructured data that they want to derive interesting insight and meaning from. Obviously, the intelligence communities don't talk too much about what they're doing, but that's where some stuff was happening. And folks like Yahoo and here at Microsoft and folks at Google were doing a lot of stuff with this, hey, I've got a copy of the internet stored on a bunch of hard drives, and I want to do something with this. And what happened here is that I needed two things. I needed a way to store this in a very scalable way cheaply, and then I needed a way to distribute the computation over that. Right? If I've got a copy of the internet sitting on a hard drive, it's actually sitting on lots of hard drives. How do I write an algorithm to go process that? And so about in 2002, Google published two interesting papers that are really just kind of good papers on the history of distributed systems to go read. But they're kind of critical in thinking about the evolution of Hadoop. The first one was the Google File System paper. And this described a system in which we could go store things relatively cheaply, redundantly, across lots and lots of nodes. And the second thing that they released was the MapReduce paper, which described a computational model to sit on top of that. And this roughly described the stuff that Google was doing internally. At the same time, folks in the open source community looked at this and said, hey, this is kind of cool. Let's start building one of these. The papers are pretty descriptive in terms of how to go build a system here. And so an open source effort started, which came to be known as Hadoop, as an open source implementation of these two papers. This is pretty typical of a lot of open source projects. Some interesting research paper, let's go start working on this. But there's something very critical that happened with Hadoop. And that was at about this time, Yahoo was looking to redo their search infrastructure. And rather than build one from scratch, they got behind Hadoop. And so Yahoo funded a lot of development into Hadoop, and is now actually running a fairly sizable Hadoop cluster on the order of 4,000 to 5,000 nodes. And they actually have a few different clusters that they're running there. But Yahoo got behind this and really started to give birth to making Hadoop, really investing in Hadoop. And so now Hadoop is an entire ecosystem. It's run by the Apache Foundation. And so this is where, if anybody wants to go learn about this, just go to hadoop.apache.org. And that's a little bit of kind of the history of how we got here. What I'd like to do now is flip over and demo how we can go ahead and get started with Hadoop, both on Windows as well as on Azure. And we've done this, we had an announcement last week where we're calling this HD Insight. And at the core of HD Insight is Apache Hadoop. We've got two ways to go ahead and get started with this. And I'll start with Azure first. So what you can do is go to hadooponazure.com. There's a link here that says is available by invitation. What this means is go fill out a form, give us your email address, and as we have availability, we'll go ahead and send you an invite code. When you get that code, come back here, type it in. We process those about weekly, and if anybody has problems with that, just shoot me a mail. Once you get the invite code to this, what you can do is walk up to Hadoop on Azure.com and provision a Hadoop cluster. This will give you a small cluster of 4 nodes. The nice thing is this is free, so that's why we're not giving you 4,000 nodes. But you can go very easily, pick a DNS name, get a login, you'll get up and running with Hadoop fairly quickly in Azure. The other thing that you can do, so this is a good way to get started with a 4-node cluster to start doing some distributed stuff. The other way is through the web platform installer. So if you go to the web platform installer and type Hadoop, we'll go ahead and there's an install here. And what this will do is this will go ahead and lay down onto your laptop, onto a server, onto a VM that you've got, a single box install of Hadoop. This is the same set of bits that will go and run on a giant cluster, but it lets you get started and start playing around with this. And so I'd encourage folks to do both of these, to run out, grab your favorite WebPI installer, and then go ahead and get HD Insight installed on your machine. So let's go back a little bit to what's at the core of Hadoop. And it's really this algorithm called MapReduce. And there's a couple of different ways we can talk about MapReduce. But really, it really boils down to implementing 2 functions, a map function and a reduce function. And so the first thing is you're going to operate on individual records. These records could be lines in a file, like a single weblog entry. It could be an entire XML file. It could be an image file that you want to process. And I'm going to operate on that file. I'm going to do some computation. And I'm going to emit a list of keys and values. The next thing that will happen is the reduce phase. The reduce phase will take all of those keys grouped together, as well as a list of all the values associated with a given key, and will hand that to you to do something with. Let's go ahead and ground this in something real. Hello world for Hadoop is something that we call word count, which is I have a bunch of text in a file, and I'd like to count all of the words. And so let's take this example. I'm going to do word count on a very simple sentence of the quick brown fox jumps over the lazy dog. In the map phase, what I'm going to do is I'm going to take that sentence, I'm going to split it out into a set of tokens. These are the individual words. And I'm going to emit a list of keys and values. Now, the keys and values that I'm going to emit are the word that I encountered and the number of occurrences of that word. And in this case, it's very simple because I'm just emitting 1. Now, the magic of MapReduce and the magic of Hadoop comes in next, which is this thing called the shuffle. Because what can happen here is, let's scale up from 1 sentence. We don't need 1,000 nodes to process this 1 sentence. But let's imagine that I was doing this over hundreds of gigabytes or terabytes of text. I would go across, each node would grab some different chunk of text, some different bit of files to start working on, and it would emit all of these. What I can do in the shuffle phase is collect together all of the same keys. So what I will do is for all of those key value pairs emitted by the map phase, I will walk through and I will pull those in so that they all get sent to the same place. So what you'll see here is now I have the has 2 values. Because of that sentence, it occurred 2 times, so it will shuffle, it will put them all together. Now, this will happen across multiple nodes. By the time it gets sent to the reduce phase is going to operate on, remember, a key, the, and a list of values, in this case 1, 1. That's going to get taken to a single node. So each node is going to get a different piece of this, and it's going to operate on top of this. And again, in the case of word count, it's very simple. All I do is sum the values of the list, and I turn around and emit those. And so what I've done is I've now computed that the occurs twice and all the other words occur once. The nice thing about this model is you'll note it doesn't have any kind of the traditional problems that trip us up when we think about parallel programming. There's no state being maintained between these things. It's very, very clean. And a lot of kind of magic happens in that shuffle phase, which is I'm going to bring all these things together because I've essentially normalized these all against a set of keys. I'm going to pull all of that together and hand it into the reduce phase. And this algorithm makes it very, if you can express something, if you can express an algorithm through these 2 methods, you can use something like Hadoop to scale this up very, very easily and scale it out across lots and lots of nodes. Let's actually dive in and kind of look at some of the code here. And this is weird. This is a bit of a first for me. I've talked at a couple of PDCs, and this is my first build. I've never led off showing Java code, so this is just a little strange for me. I just want to put that out there. All of Hadoop is written in Java, so it's kind of the first way you do a lot of this stuff is through Java. And if you squint at this, this looks pretty much like C#. Just don't tell Anders I said that. You know, there's curly braces and semicolons, and you know. But let's walk through here. I've got a mapper that extends the map, and again, here's this really important method of map. I'm going to walk through. I'm going to tokenize the strings. This is how I'm going to split these up. I can do this in kind of any number of ways. You know, this one's fairly simple. And then I'm simply going to iterate over that collection that gets returned. And again, ignoring kind of the idiosyncrasies of any one language, we can all kind of understand what's going on here. I'm going to iterate over these, and for each one, I'm going to write out that key value pair. A bunch of magic will happen. And then we will go ahead and reduce this. And again, the reduce is just the opposite of this. I'm going to get in a key, and I'm going to get in an iterable, think IEnumerable. And I'm going to sum these up, and then I'm going to write that out. So this is how I would go and write this in Java. If I want to execute this, what I will do is take Hadoop. I'm going to say I want to invoke a jar. I'm going to pass in the jar file after I've compiled that. I'm going to specify which class inside of there contains the job that I want to run, in this case word count. And then I'm going to pass it its input and output. And kick this off. This will start running. But that's how I'd write it in Java. And so I want to remember kind of that map and the reduce, and I want to start talking now about JavaScript. JavaScript's obviously a pretty important language for us across the platform, from writing client applications up into Azure. And so we want to make JavaScript a first-class language for Hadoop. And so the first way that we've done that is by letting you write these MapReduce jobs, not using Java, but using JavaScript. So let me show you what that looks like. And so the way we can do this, let's first look at how we're hosting this. Here's just another mapper that's written in Java. See, it's JavaScript mapper. It's going to extend mapper. But the thing that this guy's going to do, when it goes to map, it's not going to actually do any math here. What it's going to go ahead and do is turn around and invoke a JavaScript function. The way that we're doing this is we're hosting Rhino inside of here in order to read in the JavaScript file and bridge between the JVM and JavaScript. And the nice thing about this is Rhino is written in Java, so we don't have to worry about marshalling types across two different VM boundaries, which is kind of a fun little problem that we're choosing not to solve here. If we look at the script context here, this is the thing that actually hosts Rhino, and you'll see we've eventually boiled down into an invoke method that's grabbing this function and then invoking it and passing in the input as we go through. What this means is I can flip around, and if we look at word count, I have a very simple map and a very simple reduce. I can use all of the JavaScript isms that I'd like to here. And you'll notice that this has a lot less ceremony than the Java version. There's a lot less explicitness around types. There's a lot of just kind of leveraging the niceness of JavaScript here to go and build this. What I'd like to do now is run this guy. And again, this works pretty much the same way as what we showed here. Let's pop up just a bit. What I'm going to do is I'm going to take that MapReduce JavaScript jar. I'm going to say I want to run MapReduce JavaScript on input word count. This is a larger set. This is the text of, I think, Alice in Wonderland. And I'm going to go ahead and run that. There we go. Cannot find the file specified. Oh, I know why. Hold on just a sec. There we go. And so what this is going to do, this is going to turn around and this is going to kick off Hadoop. Hadoop is very, very chatty at the command line. It's going to tell me lots and lots of stuff here. At the bottom, you can see it finally bottoms out and says, hey, now I'm at the map in the reduce phase. And it's going to give me status reports as we go through. One thing to note here, this is a pretty good example to show this. Hadoop is not an interactive system. I'm not counting a whole lot of words here. I could certainly write a little bit of C# code to write this, to compute this very, very quickly. And so running this on just a single text file is not the best use case for Hadoop. The nice thing is, though, is that this model holds when I go from one text file to a million text files, or when I want to go and distribute this across 20 nodes. But just want to set the expectation with folks when you start using this that it's not like an interactive database where you could just kind of run a query and get a bunch of stuff back. OK, so this has gone and run. And now what I'd like to do is show a little bit more of what we're doing with JavaScript. So I've shown how we can write a MapReduce job as JavaScript. But I'd like to be able to understand a little bit more what's going on with that output. I'd like to look at that. I'd like to play around with that a little bit. And so what I'm going to do now is switch to our interactive JavaScript console. And what this is Hadoop's very command line oriented. And all of the tool set is kind of very, very oriented around, hey, I need to be able to sit physically on the head node of a Hadoop cluster, and I need to be able to submit jobs and do stuff there. If I can't do that, I'd like to SSH into the head node or remote desktop into the head node, which is fine for programmer geeks. But as more and more folks start to want to use Hadoop, especially with some of the easier things to use, that's a pretty high tax to put on folks. And it also means you have to have a machine that's set up. You have to be able to get an SSH connection. And so what we've done is we've written a shell or a console that we host inside of a web application here that interacts with the cluster. And so what this allows you to do is walk up to the cluster, view all the files here, execute command line commands. And we needed to sync to a syntax here for doing stuff. And we've used JavaScript as the syntax inside of the shell. And let me show a couple of things that we can do here. And I'm going to go to my cheat sheet real quick. So the first thing that I'm going to do is simply read in the output of that file. And so you can see here, if we zoom in a bit, hey, about occurs 102 times. So we're doing a little bit more counting here. There's a lot of things that only occur once. Let me just get right back here. We'll go back up to the top. Now, the thing that I can do here is I can take this and I can actually pull this into a set of JSON objects that live inside the browser that I can then operate on. And so we'll parse file, and then I need to give it a little bit of schema. I need to tell it what type of things to parse this into. It's very simple. I've got words and I've got counts, and count is a long. I'm going to parse this. Got to grab the data property here. And so now this has pulled back all of the records, and it's now got these as an array of JSON objects. And so what I can do with this now is I can actually kind of see what's going on with this data. I can play around with this a little bit. So I can say I'd like to have a pie chart on data. This is going to take just a little bit of time to compute because it's a little tricky. There's 3,006 unique words here. And this is kind of the way a lot of these analytic jobs work, is that I start off trying to figure something out. I get a clue at the next step. I then take that clue and I do something else with it. The clue that I'm getting here is, OK, this is really good. I can see, if I look very closely, that the occurs 1,800 times. That's not too big of a surprise, but pretty much there's a bunch of other noise here, and I'd like to kind of filter that out. And so I'm going to turn around and I'm going to run another job. I could write another MapReduce job, but we've also got a syntax here inside the console that allows me to compose a job through more of a query-based API. This is going to look familiar to kind of folks who use LINQ or other kind of fluent query APIs, where I can go build a little JavaScript string. So we'll hop back up here. And let's look at this. The first thing is you'll note pig. Everything in Hadoop, the Hadoop ecosystem seems to have something to do with animals. So elephants are the logo of Hadoop. There's the Mahout project, which is a machine learning library. The term Mahout refers to one who rides on elephants. There's Hive, Pig. There's a number of kind of names. Pig is a data flow language. And what we've done is build an API on top of Pig that I can express with JavaScript in order to say, hey, I'd like to read in all of these files. Then I'm going to order by the count. And then I'm going to take 10. And then I'm going to store these somewhere. I'll put a 2 on there because I don't remember if that's exactly it. And what we'll do here, this fires up Pig. And so what we've done is we've looked at the data. We've observed, hey, I want to refine this a little bit. I want to get it down to a smaller amount of data here. And then I'm going to go ahead and run a job on this. And this will take a little while to run. You'll see this is running here, but this is going to go and cut down the size of the data. It's going to get me 10 rows back. I can then pull that in. I can look at this. And so what we're doing here is leveraging a very familiar syntax to a lot of folks, JavaScript, in order to be able to compose queries pretty easily here and then play around with the data. As we saw with just 3,000 rows, this is not necessarily something that we want to go do and try and pull back a petabyte of data into my browser's DOM. That would be impressive if we were to go do that. But a lot of these jobs start with a whole lot of data, and it's getting it down to a manageable set. It's getting it down to whatever size. Maybe that's a few million rows that I can toss into Excel. Maybe that's just the top 10 that I can look at. And so as we get that data reduced down to a smaller set, tools like this that let me kind of play around and see the data are pretty useful. So now let's talk about .NET. We've talked about Java, talked about JavaScript. Very early on, the folks behind Hadoop recognized, realized, and kind of admitted not everyone in the world likes to write Java. And so they built a bunch of extensibility in there in order to let you bring other languages, kind of other stacks to the party. And they did this primarily through the streaming interface, something called the streaming interface. And so if you think about what we just showed with JavaScript, where there's a map function that hosts Rhino to kind of intermediate between these two worlds and throw some data over to the other side in the JavaScript side of things, streaming is very much like that. Except what it does is the contract is process invocation and standard in and standard out. It's kind of the universal communication contract understood by systems. And so you can specify any executable file, kind of throw that at it. As long as it can read ins and outs, you're good. Now that's not the cleanest programming model. That essentially means your MapReduce jobs look like void main while console.readline, a bunch of gobbledygook. And so what we've done is, and this is out on NuGet right now, we've released a library that's a wrapper on top of streaming to give you a MapReduce API. And so what I do here, I'm going to start off, create a console app, pull up the NuGet console, and the package name here is Microsoft.Hadoop.MapReduce. It's going to take a sec. I'm going to say a quick prayer to the network gods. OK, looks like we're out there. And if we go look at what this dropped into the project for me, you'll see two things. It added JSON.NET, which is something that I'll show in just a sec why we have that. And then it added Microsoft.Hadoop.MapReduce. This is going to bring in a set of types that let you actually reason about this as a MapReduce job. And so let's delete this, use a snippet here. And there's a couple of things to pay attention to here. One is mapper and reducer. This maps pretty closely. If you go on the internet and find any interesting algorithm expressed as a MapReduce job, I can go ahead and use C# for this. And the nice thing about this is that this lets me use some of the language capabilities in C#, or some of the capabilities in the .NET framework. So for instance here, rather than kind of trying to iterate over stuff, I'm simply using the sum on top of IEnumerable. It's a very simple example, but here it's where there's some very nice things inside of the .NET framework and inside of the languages that I can go ahead and use to write these. But then again, it also is very kind of similar to what I'd go write in Java. And so the context class here lets me write out counters and trace messages and log files and all of these types of things. So I can go and build a fairly sophisticated MapReduce job here. Once I've done that, I'm then going to create a class that derives from Hadoop job. I specify a couple of things on here, namely what is the type of the mapper and the reducer. And then there are 3 interesting methods here. Let's skip the first 2 for just a sec and go to configure. Configure is where I set the configuration of my Hadoop job. That command line that we talked about, there's kind of all sorts of flags and switches and config things that I can pass. We've tried to abstract the most common ones inside the Hadoop config, Hadoop job configuration type. And so I can also shell out and I can just toss in additional arguments. I can say I'd like to delete the folder, files I want to include, exclude, maximum attempts, maximum number of reducers, kind of all of these things are little flags and switches. Running the Hadoop job, you can set them here. You don't have to learn the kind of the command line syntax for that. The other 2 methods that are pretty useful here are the initialize and the cleanup. This is really common because these jobs will typically end up getting strung together, and so there may be some things that you need to do to validate your setup, or when your job completes, there's some additional post-processing that you want to go and do. And then I can go ahead and run this. And there's 2 ways I can run this. The first is Hadoop job executor.execute job. What this is going to do is this is going to turn around. This is going to create a big giant command line string, and this will go and submit this to run on Hadoop. At which point it's a MapReduce job. It'll go get distributed across all of the nodes in my cluster, and it'll go ahead and run. The other thing that we know, though, is that writing these types of things is pretty error-prone. And you saw from my simple word count example that that would be a kind of a painful F5 debug loop. Hey, let me go try something. All right. 45 seconds later, let me get to a point where I see, yes, no, it failed. Why did it fail? And so what we wanted to do was make sure that it was really, really easy to unit test these, as well as kind of make sure that the logic of this is right. Oftentimes, when you start to run these on big distributed clusters, the problems are going to be a little tougher to diagnose. It'll be, oh, out of my trillion lines of input, there are 3 of them that are causing my parser to barf. But in order to have kind of that initial part up front, just to get the logic right, we've got streaming unit.execute that takes in a mapper and a reducer. I can go ahead and pass in a set of input. It's a very basic word count again. And let me hit a breakpoint here. What I can do with this is I can just F5 on this. We've built a very tiny implementation of MapReduce that's all in memory that will just walk me through the mapper as well as the reducer. And so let me step through this. If I were to go look at this, you'll see, oh, I've now output all of my words. I can set breakpoints inside of my mapper and my reducer. I could also build up unit tests around this so that I could have a fairly good idea and debug most of the logic issues with my job before I go and submit this and run and start to have my multiple minute, multiple hour turnaround time on jobs executing. So this is available on Codeplex. The binaries are available inside NuGet. And the other thing that we can do here, there's 2 other things that I'd like to show here. The first is this is not just C# only, as well as kind of where that JSON.NET thing came in and how we can actually use types here. So we know, how many folks, is anybody an F# developer in the audience? Okay, we've got a few of them. Cool, welcome. We know that a lot of folks who are doing scientific computation, who are doing financial analysis, F#'s been very, very popular with those folks. And these are also areas where big data is starting to really make an impact. And so one of the things that we want to do here is make sure that this library is very, very friendly for folks who would like to approach this from the F# side of the world. And so We've been working with the F# team so that this library is very, very friendly here. Here again is kind of the map and the reduce. I'm not going to turn this into a my language versus your language conversation, but just want to leave you with the notion that if you're an F# developer and you're looking to do distributed computation, I'd really love it if you check this out. A lot of the things that are in a functional language like F# lend themselves very, very nicely to doing some of the processing that we'll do with Hadoop. Particularly as you get into some of the more advanced machine learning type scenarios. There's a lot of great material there. So I encourage you to check that out. The other thing that I'd like to show is if we go back to this case, what you'll see is, because streaming works on standard in and standard out, the values that are coming in are just strings. And that works really well if you're processing web logs and things like that. But as you get more complex, kind of having all that parsing code is a little tricky. And you may actually want to be able to store these things kind of in a native form. And so what we allow you to do is you can store custom types, your customer type, your weblog type, as JSON files and process these. So you can walk up to a giant chunk of JSON and you can process that. You can also use this to make sure that you output JSON so that you could go pick this up from another tool that understands JSON. We've also built this in such a way that if you don't like JSON, if you've got a custom binary format that you'd like to use, you can go ahead and extend this. So all you have to do is you can follow the example that we've done with JSON in order to insert other formats here. And what this allows me to do, this really comes in particularly in the reducer, is that you'll see that the set of values that are going to be passed in can be my custom type. So this can be my customer. This can be something that's fairly complex. And then I can operate on that. I don't have to worry about kind of always marshalling to and from strings. So just wanted to talk about that a little bit. The other thing is there's a set of tools that if you don't want to invoke it directly from here. So here we've got, essentially we do void main in order to submit the job. There's a utility that's included with this called mrrunner.exe that allows me to point at an assembly, specify the mapper and reducer, and go ahead and take care of creating kind of all this command line stuff and submitting the job to Hadoop. So we released this last week. We're going to be updating this fairly regularly. Kind of the next thing that we'll go do with this is make it very easy to submit jobs to Azure. So once I've got my Hadoop cluster up and running in Azure, be able to very easily submit jobs both from Visual Studio as well as from jobs running on the client to Azure. And essentially, you can imagine what that entails. We package that up, put that up there, and then invoke a REST API to say, go kick off this MapReduce job that looks like this. Right now, if you want to run it on Azure, you've got to move the files over there and then invoke it. So we'll go ahead and make that a little easier. So now we'll go back to the presentation. We haven't been here in a little while. We talked about MapReduce in JavaScript, and we talked about MapReduce in .NET. And pretty much it was all around this pretty basic example of word count. And so a lot of folks kind of want to know hey, OK, great, you can count words. That's cool. What do I kind of do next? What are the types of problems that kind of lend themselves to this? And some of the things to think about are, if you go back to where this all kind of came from the notion of an index of the web, reverse indexing, like anything about kind of groveling over a bunch of text, and I'd like to now go create. I've got a bunch of. Imagine I've got the hard drive full of the internet, and I would like to go and figure out for every word what are all the web pages that it appears on. I want to build the world's most basic search engine. That's the notion of reverse indexing. That takes this word count example, and it's not too much harder. Instead of just emitting a count, you would emit a count and a URL. And so you can then kind of imagine how you could go process over that, and you could create weighting and ranking. If you happen to also have a graph of how these things are all connected, you can pretty quickly arrive at PageRank, which is kind of the genesis around Google's search results. It's also really great for just doing kind of general distributed data manipulation. If I just want to clean up a bunch of data or transform a bunch of data, I don't have to write a reduce job. I can just write a map job, which you can think of as just a really poor man's way to go up and distribute across 1,000 nodes a nice parallel job. This lends itself well to machine learning algorithms and really getting into kind of the predictive analytics. There's a lot of folks who look at Hadoop and they're like, oh, it's just like a database, only bigger, which is true. And so you can certainly do all of your kind of traditional analytics looking backwards. What a lot of folks have found Hadoop very, very useful for is more of the, how do I kind of start looking at the data that I've got to start predicting behavior, not just understanding what's already happened. So on the slide deck, there's a really great book that's available for free as a PDF called Data Intensive Text Processing with MapReduce that walks through a number of these things. But what you find out with MapReduce is when you want to do some things for analysis that feel very, very simple, like a join, you actually have to do a lot of work. And so if you look at the implementation of a join in MapReduce, it's pretty tricky. And this is not really a programming model that I can walk up to an Excel user and say, hey, just go and write a MapReduce job to go join up some data. There's a lot to writing MapReduce efficiently. And so what's happened in the Hadoop ecosystem is folks have recognized that. And Hadoop has really started to become, MapReduce has really started to become kind of the opcodes of a distributed system. And what happens as we start to abstract in computer science, we start to build interesting layers on top of that make it a little more approachable and a little easier. So this is where there's things like Pig and Hive. Cascading is another example of this. And the goal of all of these is make it easier for me to do a certain set of tasks. And I'd like to talk a little bit about Hive. Everyone in this room, who can write a SQL statement in this room? Okay, just about everybody. You can walk out of this room and you can write Hive. I guarantee it. We could go get you up and running on this. You can do it. What Hive is a recognition that there's a lot of people in this world who understand SQL. And that set of people is probably much, 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 much larger than the set of folks who can go write a join in MapReduce. And so Hive is pretty interesting. It takes a syntax that feels very familiar to SQL folks. There's a compiler, and on the outside of the output of the compiler is a set of MapReduce jobs. Again, if we kind of go with the analogy of MapReduce being a set of opcodes on this big distributed cluster, a whole bunch of interesting optimization, distributed system research goes into optimizing those MapReduce jobs. And the great thing is that I don't ever have to think about that. If my data sits in a nice tabular structure like this, I can write a query that I was probably writing against my data warehouse the day before. And so Hive is something that's got a lot of momentum in the Hadoop ecosystem because it feels very, very similar to SQL. So I'd like to talk a little bit about what we're doing with Hive, and then show how we're going to surface that up and make it a little easier for a .NET developer, as well as some interesting web-based tooling for that. So I'll lead with I will lead with that web-based tooling first. If we go back to our dashboard that we install with HD Insight, we can go here and there's a very basic Hive console. And by very basic, I mean very basic. You put in a string of text here, hit execute, and we will go and run that. We're going to go and make that better. And so where we're going with this is something that will ship in a future release of the stuff of the on-prem installer, and you'll see this surface inside of Hadoop on Azure as well. And this is a web editor for Hive. And so what I can do here is, let me zoom in here. This is, again, think of Hive as really trying to project SQL on top of Hadoop. So I've gone ahead and I've created some tables. I've got a bunch of text files that basically have this tabular structure for actors, awards, and titles. This is all of the information, I think, from 1975 to 90-something about the Oscars and all sorts of various awards. And I can go ahead and write queries against this. And so let's look at first awards that Batman won. And so let's look at the Hive query language here. Select year, category, type from titles. I'm going to join on awards. What am I going to join on? I'm going to join on my key across these two things. It's important to note Hive is limited to joins on equals. If you want to do something fancier than that, it's not in there right now. It's something that's being worked on. And the thing that I'm really interested in is Batman Begins. I'd like to know all of the awards. It was a movie that meant a lot to me. We can go ahead and execute this, and I ran this earlier. Again, there's a little bit of a mind shift that happens. This isn't instantaneous. This has to go compile to a set of MapReduce jobs, which it will then go and run on the cluster. So it takes a little while, and normally I have to do interpretive dance of what a MapReduce job looks like. And the camera guy told me I can't walk out of the box here, so I can't do that today. And we'll come back and we'll see, hey, Katie Holmes won Worst Supporting Actress from the Razzies. That's the one award that Batman Begins won. But if we go back to here, we can see that, like, if I know SQL, I can go do this. And I can run this on a very, very sizable set of data. And there's some nice capabilities if we look at the data definition language of Hive in order to be partition aware. So if you think about if I've got 10 years of data, and I can write that, and I'm normally querying on some time element of that, I can write that data out in a way where it's partitioned by time. Month maybe, day maybe, year maybe. Hive can be aware of that when I go to create a table. And then so it will be smarter when it goes to create the MapReduce job. Again, kind of all of the things that we've already done with lots of other systems are happening here. Started off with this very low-level thing called MapReduce. We've built a compiler to MapReduce on top of it. Now we're building an optimizer as well. Close your eyes. We've done this with SQL. We've done this with lots of other things. And the same thing is happening in the Hadoop ecosystem. So you can go ahead and write HQL right now, either using the web tooling or you can use the command line. But you might note, hey, this looks like SQL. And we've got a way for .NET developers to interact with SQL, and that's LINQ. And so we've been working on a LINQ provider that will compile to the Hive query language. And so here I am inside LINQPad. You can see that same set of tables are over here. And we have this LINQ provider that's going to go ahead and allow me to go ahead and write this query. And this feels, this is just like any other LINQ query in .NET. So it also gives me all of the things that I'd expect out of this. So we're doing kind of the code gen behind the scenes here in order to prop up types into this thing so I can get awards. I can go ahead and find out what are, where the category is blah. So I can go ahead and use IntelliSense. I can use LINQ to express my query here. Delete this. When I run this, what we'll see, LINQPad's a nice little tool for this. We can go ahead and see this is the SQL that we compiled to. Or, I'm sorry, not the SQL we compiled to, the Hive query language that we compiled to. And so I can go ahead and use this to author my queries. This will go and this will then run on my cluster against a fairly sizable set of data. And because it's a LINQ provider, I don't have to just use it in LINQPad. LINQPad's kind of the easiest way to kind of show writing a query very quickly. But I can put this into my applications as well. And so if we go and look at what this looks like, see here, I get a Hive database. This basically gives me my execution context. I can take a query. That's the query I think that we just ran. And then we've added a couple of extensions to this that fit what I'm trying to do with Hive. So a lot of times, it doesn't really make sense for me to run a job on hundreds of gigabytes of data and kind of stream the results back to me over a pipe, like I would do with a database query. A lot of these things are kind of production jobs. They're jobs that are producing a new set of data. And so oftentimes I will, again, kind of have these staged in a workflow where I will go through and I want to output this to another table. Again, kind of something that's a very common pattern here is I'm taking really big data and I'm getting it down to a more manageable size. And so here I'm now creating the awards in 1994 table. This is a much smaller table. I may take this. I can put this inside of SQL. I could prop this up inside of my cache that's powering my web apps. But again, I'm kind of taking this giant chunk of data and getting it down to something that I can use in an online system. And all of the basic capabilities are here. We're going to keep adding to these in terms of all of the various aggregates we can support, the various join types that we can have. But you'll see that it's a pretty nice way for me to go ahead and author Hive jobs. The thing that's not in here, I'm going to be upfront, is I don't have a way to push arbitrary lambdas all the way down. What I'd really like to be able to do is somewhere here inside my select, I'd like to write a little bit of C# in order to shape the data or use something from the .NET framework to go compute something. We don't have that in there right now. As we kind of go forward with this, we're going to work to go solve that, kind of pushing that UDF, the user-defined function, kind of all the way down to the execution layer. So I just want to set a little bit of context that we don't have that in there right now. So right now the link provider will barf if you try and do that. It'll be like, that's kind of a bad idea. I can't do that today. This is not yet on Codeplex or NuGet. We're having good conversations with our friendly friends in the legal department about that, and probably in the next couple of weeks we'll get this out. But this is kind of ready to go, and we'll get the code up on Codeplex to kind of party on this. Okay. And so the other thing that we'll do is, as we kind of have upcoming releases of the service inside of Azure, as well as updates to the on-premises installer, we'll bring in that web authoring experience as well for the Hive queries that will have IntelliSense shortly. So really, what we're trying to do is make it really, really easy for folks to get started with Hadoop, kind of solving some of these big data problems. And we want to do this in a way that lets you use the tools that you're used to using. Biting off Hadoop and big data challenges is enough. If I also have to give up the IDE and development environment I've been using for a while and pick up this strange Java thing, and that's a tall order. We really want to make it so that like language choice development platform is not a barrier for you to get up and running with Hadoop. The other thing that I'd say, and this is interesting, I really don't want this to ever be perceived as a C# versus Java conversation. This is really, we want you to use the tools that are familiar to you and that you're most productive in. We really want to kind of lower that barrier to entry to get you playing with this stuff. And we think that there's a lot of win there. We think that that's super, super useful to get up and running with Hadoop, write your jobs in a language that you're familiar with, use tools that you're familiar with, whether that's things like Link, whether that's Excel, in order to process the data so that you can take advantage of the fact I can now store this data pretty cheaply, either on premises or in Azure, and I've got a way to actually process this and ask questions of it. And so kind of after this, I'd love if you'd go check out HadoopOnAzure.com, request an invite code, as well as go to WebPI, type in Hadoop, and get up and running. If you've got any questions, my email address is mwinkle@microsoft.com. Go ahead and shoot me a mail. I think I've got a little bit of time in this room for questions, and then I have to go to some other room where I'll be at to answer questions as well. So thank you, everybody, for coming. And if you got questions, fire away. Please step up to a mic, though, so that they can get recorded.
Hey, can you show us a little bit about how the mapping process works to get a Hive query working against your sort of textual data?
Sure, sure. Yeah. Switch over here. So essentially, and I don't actually think I have any of it here. Basically, I've got a set of files sitting down on disk. There's a create table syntax that looks just like SQL, but at the end of it, we append onto that a little bit of physical stuff, which is where on disk do these files sit and what format do they have. And so all of the basics like comma separated, tab delimited, blah, 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 that all works. You could stick a custom formatter on top of that. But the interesting thing about Hive is it essentially is schema on read. So it allows you to define a schema, and it just trusts that the data is in the right shape. As it reads, it will go read it up through the pipe, and it will say, hey, you told me that it has these columns. You told me it's comma delimited. OK, here's your rows. And that's what gets passed into the system. So, other question?
I had some confusion. You were talking about, at first, reading words out of a file, and then all of a sudden we're talking about tables. So
Yeah.
I don't understand what the table is, and then...
Sure, yeah. The table is just a projection of a tabular schema on top of a text file. In this case, all I've got is a text file that just has, movie ID, comma, actor ID, comma, name, comma, award count. That's all that's in there. Hive lets me walk up to that and say, hey, what you actually have is comma-separated values, movie ID, actor ID, name, and award count. That's your schema. Now, the difference between that and a database is that I can define that after the fact. I can just have the file on disk, and I can say, hey, here's the schema. And it also won't attempt to validate that up front, which means I can load data into the system really, really quickly because I don't have any integrity checking. But it may mean on the other side that there's a problem coming back up. And when after this, I'll sit down and I can pull up some more examples. If you look at Hive DDL, the create table syntax makes that pretty clear. Yeah.
I kind of have two questions.
Okay.
First of all, will HD Insight scale out to a heterogeneous cluster? For instance, can you run clusters in Amazon and have them communicate and cooperate with a cluster in Hadoop?
Yeah. So the general answer there is that Hadoop itself is not really designed for cross data center work. It pretty much assumes that all 1,000-ish nodes are sitting in the same, basically on the same general backplane from a networking perspective. If you were to try and do it cross data center, assuming you could get all of kind of the communication protocols to kind of talk from a node sitting down in Amazon to a node sitting down in Azure,
right?
There's nothing blocking that scenario from working. It just would not be the most efficient utilization of Hadoop, and that's not really how MapReduce or HDFS has been designed. So you'd run into some issues there.
Right. The second one is, can you give us any guidance in terms of data size, or when does it become efficient to start using Hadoop against data?
Sure.
Are we talking about 10 gig, 500 gig?
Like any question around kind of perf or size, it depends. It depends what you're trying to do with the data. It depends on kind of the questions you're trying to ask it. Depends on, is that data just sitting there? It really would be scenario specific. We've got one customer, for instance, that operates a fairly sizable Hadoop cluster on only a gig of data. But what they do is they read that in, they then spawn off a ton of different Monte Carlo simulations to go expand out to a whole lot of data, to then go and find the 5 interesting occurrences in the model that they want to analyze some more. And so that's why it's really tough to kind of give individual guidance about, at size X you would go use Hadoop.
Right.
It's a little more scenario specific. Okay.
It seems like there's an overlap here between the Hadoop and the Hive and linked to Hive and things like that with the Dryad. And I don't know if you could speak to that in terms of strategy Microsoft has on their Dryad shipped platform and what they're doing with this as well.
Yeah, so I'll refrain from commenting on larger Microsoft strategy stuff. Really kind of what this is about taking Apache Hadoop, which is kind of gaining a ton of momentum and making sure that it's a first-class thing running on Windows. We really would like Windows to be the best platform to deploy, manage, and scale Hadoop. And so that's really kind of what my team spends a bunch of time on. So,
is this useful for CPU-heavy, not very data-intensive workloads?
Yeah, it can be. So Wenming, I think he's hanging out in the back somewhere. Did he leave already? Okay. there's a gentleman in the back who also does a lot of high-performance computing type stuff. He'd be a really good guy to kind of follow up with. Again, kind of, you can use Hadoop that way for fairly CPU-intensive things. I think the thing is, you have to figure out what's the right way to express the job that you want to do. If it's tabular data warehousing stuff, Hive is the way to go. If you've got a distributed algorithm that's expressed as MapReduce, that's good to go. You can get Hadoop to do other things like spawning up daemons in all of the nodes and kind of doing inter-node communication. But at that point, you're starting to do a little bit more work. If you've invested in a Hadoop cluster, then that may be a perfectly fine use there. Depends. Okay, time for a couple more questions, and I think I'm going to go somewhere else. Yeah.
What about if we need more than 2 servers on Azure? Can we spawn more, paying, for example?
So you will be able to. You can't right now. As we move to general availability, we'll allow you to scale out to whatever cluster size you'd like.
Do you have a time frame? 1 month, 2 months, 1 year?
I'll also generally refrain from timelines. No, so we've been updating the service every month. We keep updating the service. We're working towards a GA of that service in the next calendar year.
Okay.
But what I would say is, I'd encourage you, if you've got a scenario where you want that today, shoot me a mail. We can talk about it.
It's Matt W at Microsoft.
mwinkel@microsoft.com.
Your initial, then the surname.
Yeah,
Okay.
Without an R. They ran out of R's that day.
Without the last letter.
Yeah, hold on.
Okay.
First slide. We'll get there. Right there. So
Okay.
that at Microsoft.com.
Okay.
So,
Thank you.
okay, and I'll be in the other room after this. So thanks.